Good afternoon to everyone. I welcome all of you to the 49th lecture in the lecture series in Nonlinear Dynamics conducted by the Department of Nonlinear Dynamics, Bharathidasan University, with the support from RUSA 2.0. I'm happy to introduce today's speaker, Professor Serhiy Yanchuk. Professor Yanchuk is working as a research scientist and project leader at Potsdam Institute for Climate Impact Research at Humboldt University of Berlin. Professor Yanchuk has obtained a PhD in mathematics in the year 1997 from the Institute of Mathematics, Kiev. He then worked as a research scientist in the same institute about 5 years and moved to Berlin as a postdoctoral fellow in the year 2002. Professor Yanchuk was working at different capacities in Humboldt University, Weierstrass Institute and Technical University in Berlin. Recently, he has observed as project leader at Potsdam Institute for Climate Impact Research. He has more than 10 years of teaching experience. Currently, he is supervising 7 PhD students. Professor Yanchuk is one of the active researchers in nonlinear dynamics. He has won several awards and recognitions for his research contributions in nonlinear dynamics. He has been invited to several European countries in connection with his research. He got mobility grant of the National Research Council of Italy in the year 2014. He was also the founding member of Easy Math. During the last 5 years, he has secured 2.8 million euros as research grant. Professor Yanchuk published a large number of publications in which several papers have come out as editor's suggestion and highlights. With this short introduction, now I invite Professor Yanchuk to deliver his lecture. Over to you, Professor.
Okay, thank you very much for your kind introduction, Professor Saint-Yves. And it's my great pleasure to give a talk here to this very great community. And I'm very happy really to talk here with some our well-known colleagues from India and also to the younger students. So please, if you have questions, you can also interrupt me during the talk. You're very welcome, because the talk will be probably not longer than 45 minutes, at least the way I prepare it. So it's completely fine if you have some questions during the talk so that we understand better. Yeah. So the main idea of my talk today is to explain you how we apply different delay systems, delay differential equations for certain machine learning tasks, including deep neural networks here, as in the title, but also I will mention something about time delay reservoir computer. I know this is nonlinear dynamics seminar, that's why I would like to put more attention on dynamical systems, on dynamical aspects, and a little bit less attention on machine learning. But of course, I will try to explain also some of the machine learning tasks, especially for younger students, probably that they understand the main ideas. Okay, so my main co-authors on my way on machine learning and dynamical system mixture are Florian Stelzer. This was my PhD student. He's now working at in Tartu, Estonia. Andre Röhm, he is now at Tokyo University. Raoul Vicente, he's a professor at University of Tartu, Estonia. Ingo Fischer from Palma, Spain. Kathi Lüdke, she's a professor in Ilmenau in Germany. Felix Köster, he's a PhD student from Germany. And Mirko Goldmann, he was my master student, but now he's working in Palma in Spain. So these people, we did a couple of publications and in this topic, and I will mention also some results from these papers. So let me start. Yeah, so, okay. How do I? Yes. So the outline of my talk will be, I will first explain you how we construct the reservoir computing system with some delay differential equation, delay system. And then I will explain you how one can emulate arbitrary networks with a single delay systems. And then afterwards, I will kind of the next level, explain how we implement deep neural networks. So this was shortcut DNN by a single neuron or a single delay system. That's just synonym in my talk. And then I will show you some examples of applications to some benchmark tasks. And of course, during my talk, I will pay attention mainly on a lot on dynamical aspects. So, and you are welcome also to ask some questions. So if something is not clear. Okay, so now this is a time delay system, I consider, in a very general form. So please don't be afraid of the long system, because I will explain you in all details what it does mean. Yeah. So this is a system with time delay, the differential operator, so derivative, equals to some function which depends on x of t. That would be ordinary differential equation. We have additionally z of t, which is accounts for an input. For example, time-dependent force, external force, and this will be a term through which we input information in our system. We have also delayed terms. Yeah, these are the terms which makes our system time delayed. And with several delays, x of t minus tau 1, tau d. Additionally, we have a modulations of these delays, and with these modulations will play important role also. So basically, it's the system with modulated time-delayed feedback in a general form. This form I will use for several times later. But just to mention, for practical realizations, we use a specific form of such system, which is written here. Yeah, so this is just a specific form of this equation. And this is just x dot of t equals to minus alpha x of t, a very simple relation with respect to non-delayed coordinate x of t, plus nonlinear function of this combination a of t. A of t here is a linear combination of the input signal z plus some of the delayed terms which are modulated by the functions mt of t. So that's a of t is called also activation function, f of a of t. So that's the activation. This is a bit simpler version of the previous form. And the nonlinear function f can be chosen as some nonlinear function. Maybe you have heard about Ikeda model, nonlinear model, or Mackey-Glass delay system. So these functions can be taken from these equations. Okay, so let me mention also one more detail. This delay system usually can be solved provided we give some initial conditions. And these initial conditions are usually are functions, x of s. This is in contrast to ordinary differential equation. For ODEs, we give just 1 point. For delay system, we provide some history, x of s, on an interval of the maximum time delay. So minus tau d is the maximal time delay among all delays to 0. So this is a history interval which one must provide to solve the system. However, if the functions, the modulations functions m1 till md, they are specifically chosen such that they are 0 for all times smaller than tau j, for all times smaller than time delay, then we don't need such a history function. So basically, the terms which refer to the history in this equation, they are put to 0 by choosing the modulation function. And this is what we use for our application in deep neural network. So we just choose a specific modulation function such that we don't need to provide a history, and we don't have a problem with the history for time delay system in our case. So that's why just x of 0 is sufficient. And to solve this system is just equivalent to solving some ordinary differential equation system. Just give initial condition x of 0, and then we solve the system. Okay, that's regarding the class of systems, dynamical systems we consider. And then let me start with, now to go in the direction of machine learning, I start with the reservoir computing, and then this will be the first point. And then I go to deep neural networks, DNN. So in fact, the understanding reservoir computing will help also to understand DNN, because that's a lot of things are used also further. So let's start with reservoir computing. This slide is a little bit busy, but I will explain you kind of all components. So the figure here provides us a basic idea of the reservoir computing. In the reservoir computing, we have the input U. You can assume some handwritten digit, like we write at some digit, like 4, and as a picture input in the system. The system is called a reservoir, and this could be a very complicated dynamical system. Usually, classically, it is some network, which is given by the nodes and connections, and there is some dynamics on the network. So the input is given as an input in this network. And then we read out a state of the dynamical state of the system. In here, it's given by x1, x2 to xn is a state of the nodes. And we compose a linear combination of the state of the network, yeah, and call it y hat. The linear combination is with certain weights, wi, which are then subject to the learning. Yeah? So this is wi is something which will be kind of adjusted to get a proper input-output relation. So the main task of the reservoir computing is for the given U to provide a correct y hat. For example, for the handwritten digit recognition, U can be a picture of our handwritten number. Like if we write number 1, we just send to the system a pixel by pixel picture of this handwritten 1. And then for an appropriate weight, wi, we should get y hat, which is probably a vector from 0 to 9, where you have zeros everywhere except 1. So on the first place, you should get 1. And this would provide us a correct classification, the input U to output y hat. And so the main idea of the reservoir computing that one has some tests, input-output pairs, and using this input-output pairs where we know the correct answer to train the system to train the weights wi. And these are called readout weights w, which are trained. In the reservoir computing, it's important that the reservoir is fixed. So it's just a given, let's say, network of dynamical nodes, which is fixed, and you don't have to train it. You train only w. So then once more, the goal is a given input U, the picture, approximate the mapping U to Y, so to provide by some value Y hat, which is a correct answer. So one examples of the tasks, one example I already mentioned, it's the second one written here. If we have some image of the written digit, we have to give as an output the correct answer of the digit. Other tasks could be, for instance, if we have the input chaotic time series on some interval from 0 to t, and we input this time series as u in the reservoir, then the reservoir should predict the time series on the next interval, for instance, on the interval from t to 2t. That would be another example of a task. One more example could be, for example, if we put as an input a random number sequence, just uniformly distributed, the reservoir should give the same sequence shifted in the past. Yes, for example, the reservoir should remember which random number should be given, have been given as an input in the reservoir some times ago. And this is called recall memory or memory capacity of the reservoir. So in this way, one can measure how the reservoir remembers the numbers. Okay, so that's basic idea about reservoir computing, and the basic ingredient here is a dynamical system reservoir, which is typically a network. Now, the basic idea of the deep neural network, it's actually the goal is the same. We have input U, and we want to approximate some output Y hat, which provides us a task, the solution for the task. However, in this case, and contrast to the reservoir, we have a dynamical system, which is a network. In a specific realization, in classical realization of deep neural network, this network is unidirectional, like feed-forward, and consists of several layers, like input layers where the input is coming, and then we have the next layer, all these internal layers, they are called also hidden layers. And then we have an output layer which kind of sum up the information and gives us the output. So that's also called multi-layer perceptron, this setup. And in contrast to the reservoir, all these connections have also weights. So not only the output, like in the reservoir, but also internal layers, hidden layers, they are connected by some weights. And these weights are also trained in the deep neural network. And this are usually computed using the backpropagation algorithms. And usually such networks is implemented using the maps. So all these lines are application of some discrete map. Okay, so these are basic ideas of reservoir computing and deep neural network. So now let's come to my kind of more specific topic. I would like to speak about delay system, how these things can be implemented using delays, just one delay system. And I start with time delay, reservoir computing. So you see again basically the same schematical picture of the reservoir. We have input, we have a reservoir, and we have output. And this is an example of classification tasks, like in case the output layer classify the written digit as 2. Just an example here. In time delay reservoir computing, there are some specific features, and these features are as follows. So that the input layer must also transform the signal into just a temporal signal for the input, which is like we have only one point of the input in the delay system. That's why we transform this to a single function, which depends on time. The reservoir is based on time delay system, and that's why we have just here we can schematically plot the delay line as it would physically exist. For physical applications, also the delay lines also exist physically, like delayed feedback in the laser, they exist as a delay line. So this we show it also here. And the delay line can be splitted into the nodes with certain distance, theta, and these nodes can either physically exist in the physical delay lines, or we can imagine them as a time-shifted values of the state of the reservoir. And that's why these nodes are called virtual nodes. So let me then give you more details about reservoir. So basically, in a very kind of rough summary, the reservoir makes the following. You have the input U. The input U is mapped into the state of the reservoir, X, and the state of the reservoir leads to our output, Y hat. So just roughly. We extend a little bit this very basic scheme, which can be applied for any machine learning, by one step more. So we have input U. From the input, we make the time-dependent input Z of t, which is then appropriate to enter as a force of the delay system. And then this leads to certain state of our reservoir, of our delay system, x of t, and then it leads to the output. So basically we have 1, 2, 3 steps, which I would like to explain now in a little bit more details. The step 1 is called preprocessing, what we call. The step 2 is basically the reservoir, and step 3 is readout. So let me start then with step 1. So this is how is again this map of our reservoir, the action of the reservoir, and let me explain the first step of delay-based reservoir. So U is given usually as a vector, discrete vector. For example, if we have written digit as an image, then we have pixels from this image, and we can order all pixels of this image in one big vector U. And then we have just vector U of probably very long dimension, or maybe not very long. Some benchmark tasks of handwritten recognition, they are not very of very high resolution. So this is kind of not too long, big vector U. Now let me explain how this vector U, discrete vector, is transformed in the time-delayed reservoir computing into some function Z of t of time. And we will do it with this picture. Basically, we have some clock cycle t. You see 0, t, 2t, and during each clock cycle, we have an input of one component of the input vector. So here you see the blue line, U of 0 is the input of one data point. Here we see that the next data point comes in. Additionally, we remember we have, okay, this is a new information. So additionally, we split the clock cycle into several sub-intervals with length theta. You remember this theta, the distance between the virtual nodes. And at each theta interval, we multiply this U of 0 with certain weight. It will be W1, here it will be W2, W3, W4. This is an example that we have just 4 virtual nodes. So that's why we have 4 input weights, W, which are very often randomly kind of assigned these weights, W1, W2, etc. So now instead of this blue line, we have the red function. The same also for the next interval. We have, we multiply now the next data point, U1. So basically we have this red function, which is a step function, which we call Z of t, and this function will be given as an input to our reservoir. So this is how we do preprocessing of the discrete vector into the time-dependent input function. Okay, so that's, we got Z of t. The next step is given a Z of t, the input function, we compute the reservoir state x of t. And that's for us, for like theoretical side, it just means we have Z of t input function, we compute a delay differential equation of this form, for instance. This is a simpler form I have chosen. We just solve this reservoir differential equation. For physical setup, this would mean that we given Z of t as an input to our like laser system, for instance, we get some state x of t of our laser system. Here, different realizations are possible and exist in time delay reservoir computing. I just mentioned a few dynamical aspects of this of this process, because this is basically a delay system with an input. That's why a few remarks that if we have small inputs, z of t, which is also often the case in applications, then it often leads to the dynamics close to an equilibrium of this delay system. And then you can compute like the properties of this equilibrium, the eigenvalues, the spectrum, and then this spectrum plays also important role for the functioning of the reservoir computer. So this is where the nonlinear dynamics comes into the play for helping us to understand how reservoir works. The further remark is that the reservoir, or this process of input and X output, should possess certain property which assure that for different inputs, or for the same input, the reservoir gives you the same or similar output X of t. And this is called generalized synchronization in nonlinear dynamics. So it's interesting that in order for this reservoir computing to work robustly, the generalized synchronization should take place for this system. And that's again where nonlinear dynamics comes into the play. And this generalized synchronization for the reservoir computing also can be measured by, for instance, conditional Lyapunov exponents. There are also certain resonance effects which take place here between time delay tau and clock cycle. You remember z of t was composed using the clock cycle, and this gives you some internal periodicity features of z of t, which then interplay with time delay. And this is again interesting, like research question, which, for example, can be studied, and one can see that as soon as you have resonances of between tau and clock cycles, then the performance of the reservoir decreases. So that the reservoir doesn't like resonances, at least in this case. So let me then continue. The next step will be, or let me check. This is another illustration of how dynamical features of the reservoir affect the performance. Let me then show just an example of, here you see an example of certain two-layer reservoir computer. I don't want even to show the equations, but because I see that I become too long in the time. It's just a certain bifurcation diagram of certain delay system which is acting as a reservoir. And then we compute also conditional Lyapunov exponents for the same delay system, which are shown here in a color scale. So in the white regions, there is no generalized synchronization. In the colored region, there is generalized synchronization with a certain degree. This is also related to the bifurcation diagram. And then if we compare with the reservoir performance, just in our case, we compute the reservoir performance using the memory capacity. So using like how the reservoir remembers the random numbers. And you see that this performance is very nicely related to the conditional Lyapunov exponents of the reservoir. Like if you see that the performance here is better if we have like yellow color. If we have a dark color, the performance is bad. So you see that the bad performance corresponds to the absence of the generalized synchronization. So basically this dark colors means that we cannot use it as a reservoir. Okay, I see that there is some question. What is I wasn't able to read, so can you please
you can read, or let me read.
Yes, please, because this somehow...
What is beta 1 and beta 2?
So beta 1 and beta 2 are certain parameters of the reservoir. I even don't... So let me... sorry. So this is a function, is some reservoir. In that picture, we have more complicated reservoir which is composed of two such equations, like two layer, and beta 1 was a coefficient here, beta 1, which multiplies this f, and beta 2 was a coefficient which multiply the nonlinear function of the second layer. So sorry for not showing you a specific example, but these are some parameters of the reservoir which are not important here. So that the delay equation depends on the parameters, and here are some parameters which has, I don't want to specify which parameters. It's important only is that there is a relation of performance and the dynamics of conditional Lyapunov exponents. So here's just a short reminder what are conditional Lyapunov exponents, maybe for students. Yeah. So if we have a system with an input, okay, here I write ordinary differential equation, but the same for delay. Input Z, this is the same that we have. And if we have a copy of such system, then the distance between the two driven system x1, x2 with a given signal Z of t is proportional to like exponent with conditional Lyapunov exponent. Yeah, and so if the conditional Lyapunov exponent is negative, then x1 and x2 they converge to each other. So it's just a synchronization with the common external signal. This is conditional Lyapunov exponent here. So once more, the main message is that dynamical analysis, which I cannot kind of explain you in all details here, conditional Lyapunov exponent bifurcation analysis is very much influence the performance of this machine learning system. So we start to understand how it works, this reservoir. Okay, now let me try to explain the last step of the reservoir computer is how we get from the state of the reservoir x of t to the output function. And that's easily, it's just a linear combination of the values at the nodes. So you see this is again the clock cycle. And if this is a solution of our delay system, we cut the clock cycle by some interval of the length theta and get these virtual nodes. Virtual nodes are some values of x of t of our solution of our reservoir at a certain moment of time, and the distance is theta. So we just compose discrete vectors, x of 1, and then x of 2, x of 3, which correspond to each clock cycle interval. And then we just multiply this discrete vector x of 1 with random with output weights wj, and so this linear combination can be just written as a multiplication of the vector x of k and certain vector w of weights. And this can be given for all clock cycle intervals. So this is written as an output from the clock cycle interval k. We have y hat of k. And then from all clock cycle intervals, we get some y hat vector, which is a linear combination of all x discretized with weight w. So the main point here is that the weight w is trained using so-called rich regression, which is basically a least square. So w is considered as a minimum. So such the w is found to minimize this least squares problem. And there is a solution. Yeah, the rich regression problem has an explicit solution, which we have here. I see there is a question, but maybe let me finish this 2 points, and you can ask the question immediately. Yes. So basically, what we have here for the given input y, for the given input x, basically, no, for the given input u, we compute x. And if we know output y for our training example, we just explicitly, using this formula, we just explicitly find weights using this formula. So if we have the training data, we immediately get weights for our system. So that's why it's so simple to train the reservoir. So maybe there was a question from Fernando.
Fernando?
Yes, thank you, Professor Yanchuk.
Yes.
My question is, in the pre-processing phase, you have used W.
Yeah. That's
here also W, but it's a coincidence,
true.
no?
That's true. That's different W. Thank you. That's very good remark. I'm sorry for using the same letters. These are different W's. Yeah.
Okay.
We want always to call weights W, and in this case, I somehow overused this rule, and that's true. This W are output weights. These are different from the W of input weights. So for the reservoir, usually the input weights are assigned randomly and kept fixed for all the time, but the output weights are trained, as I mentioned here. Okay, thank you for the remark. So that's, you see that questions are very useful to correct me. Oh, please, you're welcome to ask more. Now, this is an example of the reservoir. It's just one example how we, by appropriate choice of the parameters, we can nicely predict the chaotic time series. I mean, there are many other papers, just mentioned our results, just to take the figure from, but there are many other papers also of chaotic time series predictions from the reservoir. Sorry for not mentioning them in the papers here. You see here just a given time series as an input, which is just a red line, a red kind of pulses, points. We predict correctly, and these are the blue points, which are actually almost matching the red ones. And the error here is given by the blue colored dots here with a scale here, which you see that it's very small, like prediction error is very small. But it's just to mention that reservoirs are useful and can predict chaotic time series. In this case, it's a Mackey class time series. So this was kind of a small excursion to the reservoir computers with delay systems. And now let me try to mention the remaining time. Just let me check the time. Okay, I'm actually slower than I expected. But in 1 hour, I will be finishing that for sure. So this is a deep neural networks, and we already have some information which I will exploit in introducing the deep neural networks with a single delay system. We call this this scheme or structure for building deep neural networks from delay system as a Fit-DNN, folded-in-time DNN, because in fact what we have is a network which is existing in time and not in space. So let me just first, motivate. Why do we want to build such networks which do not exist in space but in time? The first motivation is that direct hardware implementation is apparently scaling have some scaling problems. Yeah? So if we want to implement each nonlinear element, each network node, then that's additional physical node. And modern deep neural networks can have millions of such nodes, and usually highly similar elements are needed. And that can create problems. So how to implement millions of physical chips on chips as nodes, that's difficult. And even more, the number of weights, it scales quadratically. If we speaking about like all-to-all coupling, then it's quadratically. And so that could be also a problem, and especially if you have a two-dimensional processing on a microchip, that could be not enough space. And here is just some example. Maybe there are even newer example. This one is from 2017. We see how the nodes in a deep neural network are implemented on the chip. So you can count approximately how nodes are here. And I guess in this example, there are 22 nodes in one layer. And that's already kind of very challenging tasks. So that's why we would like to build a network which consists just from a single node. And this is a conceptual model. We have an input here, similarly to the reservoir. There is some input weights, and we produce some function g of t, which is similar to the reservoir, like a time multiplexed function a of t. It enters the activation function a of t, similarly to reservoir. This is a delay, our delay node, which produces the state x of t, and then it goes into the output multiplied by the output weights, and we have y. So very similar to the reservoir, but what we have additionally is that we have multiple delay loops, tau 1, tau 2, tau 2 delays with certain modulation functions, m1, m2, and d, which will play also important role. There is also a standard bias, but I will not pay a lot of attention on this. This is a typical for machine learning and doesn't really important for, or qualitatively important for dynamics. So let me try to explain you. Okay, this slide is quite full, but I try to explain you. And we have many concepts already introduced in the reservoir case. So this is our delay model with modulation delays. So what we have here again is a clock cycle. You see, if that's a solution of the reservoir, we have now again clock cycle t, first clock cycle, second, etc. So we split the solution into the intervals. And then we additionally split into the virtual nodes with internode interval theta, the same as before. So the virtual nodes x, k, l is just values of x at a certain node. L is the layer and k will be a node within the layer. So basically what we will have is that the clock cycles will lead to the layers in our network. So the nodes are clear, these dots, the x, k, l, but the links in our network will be a functional dependence. So if, for example, we have a node x22, so this layer 2, the second node in layer 2, then if we have a time delay, a certain time delay, which is commerciable with theta, then we have a delayed connection through some previous node from the previous layer, for example. And that will give us a functional connection, a link in our network. So that's how network appears. And we show it schematically here. For example, this is again clock cycles, and the arrows show exemplary how time delay tau 2, for instance, creates a link between that node and this node. Another time delay tau 1 creates another link, and there are many links between many nodes. So what we do here, additionally, we remove the links which are not between the neighboring layers. For example, we have this tau 1, and it goes from the previous layer, from one clock cycle interval to the next one, like here, so we keep it. But if it is inside the layer, we remove it, and we remove it by setting m equal to 0. Yeah, so you see that this modulation function, if it is 0 at a certain time, then we just don't have this connection. And this is a way how we guarantee that we have just interlayer connection, just to get a feed-forward DNN, as I mentioned in the beginning. So what we have as a next, we do the following. I just repeat the picture I have, and now what I do, I cut the clock cycles and I just plot them beneath each other. So like here, I just cut and I keep all connections as before. So what I do now, I will just rotate that picture. I just rotate it a little bit, stretch it so it doesn't look nice. So I will correct now. It looks nicer here. And I additionally also plot the input connections input layer and output layer. Everything else is just equivalent to what we have here. And you see actually that it is in fact a feed-forward network which will emulate or which will act as a DNN in our case. So let me now summarize a graphical summary of our Fit-DNN. So this is how it looks like in temporal resolution. We have input in the first layer and output from the last layer. Everything in between will work as the hidden layers, and that's how we can represent also graphically as a network. And importantly also here is that the modulation functions MD of t, they will determine the weights on each arrow. So we can kind of control the weights along the arrows in the network, also in the hidden layer. So our M of t weights will play the role of weights. Modulation function play the role of the weights. So this is so this is a graphical summary. But now let me show you how we can explicitly compute like this errors, or what does it mean? So we understand graphically, but like with the formulas, we can get it more explicit. Just let me check shortly the time. Would it be okay if I speak like more 10 more minutes?
Yes,
or?
yes, sir. Yes, of course.
Okay. So thank you. So and please, because I might skip the kind of messages in the, so please, if somebody has a question, just speak.
Okay.
Yeah. So let me now. This is a graphical picture of our network, and you see this is kind of DNN, but how it can be computed explicitly. And let's start with the next slide, which is again a bit busy, but I will explain you that. So what we have here is actually the delay system I wrote you from the very beginning, our delay system, but which is just discretized using Euler scheme. Yeah, so I just substitute the differential, the derivative by a difference xt plus theta minus x of t divided by theta. Yeah, and this is Euler discretization scheme for our delay system, nothing else. And I use here the step size theta. That's why what I'm speaking now about is about small theta. We consider small distance between the virtual nodes so that we can get a direct map from one node to another node, as we see here. So what we add here, the next is that let us rewrite this equation for the node. Yeah, so we take the t plus theta is assume that it is at the same at certain node n at the layer L. Then x of t will be just a previous node, just xl at the node n minus 1. That's just a previous node plus theta f. And then x of t will be again the previous node. Z of t will be the input signal at this appropriate time, which correspond to this node. The modulation function at this time, which we can determine as we want. Yeah, this is our freedom. And then x of t minus tau 1 is actually, okay, this is our node, previous node, but also minus delay. We assume that all delays are kind of resonant to theta, that they're commensurable to theta. That's why we have some integer number n tau 1. And if you remember previously, I assumed that we are connecting, by delay, we're connecting the previous layer. That's why this value is actually a certain node in the previous layer. So it's xl minus 1 layer with certain position, which I don't specify here. And also here, we just delay t minus tau d give us also another node in the previous layer, xl minus 1. And the values of the modulation functions are just some weights, which we call here V, L1, some indices. That's just to know that these are weights which we can change. Graphically, the coupling between the layers. So you see this picture again shows that one layer, another layer, and there are some arrows. And these arrows can be illustrated by some adjacency matrix, coupling matrix. And this adjacency matrix will look like this. And we have for time delays, which are equal to the clock cycle intervals, we have the whole diagonal with weights. And these weights are given by the modulation function. So they all can be different. If we have time delay which is smaller than clock cycle, we have some diagonal, some line above the main diagonal. And for time delay larger than clock cycle, we have a line below. So the one time delay leads to the whole line of connections between the layers. And all these lines can be populated by some weights. So it's important that these weights later we will use for the training of a system. Okay, so this is how one can explicitly, like very detailed, get the access to all this connection in the network. And this is possible for small theta, as I mentioned, for small inter-node interval. The same explicit and relatively simple expressions can be obtained for another case, the case when theta is large. Yeah, in this case, we get networks for large node distance. We can do the following. Yeah, and here I use a delay system of a simpler form. This is now not a general form, but simplified form where we actually work with. This x dot equals to minus alpha x plus activation function of delayed and input. And the main point is that if we have the inter-node interval theta large, and you remember that delays are commensurable with theta, then it's basically leads to the fact that delays are large. So t minus tau d, all tau d are large, larger than kind of like all other time scales in the system. In this case, I make it short, but maybe someone who kind of have experience with delay system knows this, that we can rescale time such that we have, instead of delay tau d, we have a delay tau d rescaled by tau maximum. So rescaled by time by tau max. We have now all delays smaller than 1. So if tau d is tau max, we have just 1. For all others are smaller. But also we have 1 of tau max here, which is a small number. Now, you remember that we have a large delays. So we have a large tau max. So this is small number. And for certain cases, so of course, what I say now is not rigorous. It holds only for certain cases. But for certain cases, we can say, okay, this is small number, so we can neglect this. It's a kind of adiabatic elimination, which works only in certain cases, but in our case, it works. So we can put this neglect, put it to 0, and then what we have here, we can solve with respect to x of t. And we have here, and what we see here is called usually map limit of delay system. So it's just a map now. So we know delayed values, and we get just a x of t. And what, instead of solving delay system, we just iterate the map. Yeah? And that's now explicit map, which we can rewrite with respect to our discrete x, with respect to our virtual node. So instead of like continuous x, we just write now in terms of the layers. So the vector of all x in the layer L is given as like 1 over alpha f of x in the layer L minus 1 with a certain weights. Yeah, and the weights I already explained before. And this coupling matrix can be made arbitrary in our case using like arbitrary appropriate M modulation functions and sufficiently many delays. And that's why we can have arbitrary topology. And this shows also that since with our system, we can get such a system with arbitrary weights, That's actually the system which is classical multi-layer perceptron, MLP, this classical DNN, or simplest case. And that means that with delay system, we can realize arbitrary multi-layer perceptron, which is already kind of interesting. Okay, very shortly on the fact that we can train the weights, because that's very technical, complicated, but in a very short, we can define a loss function, a certain functional, for example, for the classification tasks like handwritten digit recognition, we can introduce a cross entropy function. Here, yp is a given known output, and yp hat is the output which is given by the by our system, and that should be minimized for the optimal performance. Or for other tasks, which I mentioned very shortly later, for denoising task, we use mean square error functional, like a difference squares of differences between the approximation and exact, and it should be clearly also minimized. So all these functionals clearly depend on the weights, and then the gradient descent scheme is used to minimize this functionals. So this is a very general gradient descent scheme. So new set of weights, all weights, is an old set of weights minus certain training rate and gradient of a functional, either this functional or another functional. And the main technical thing is, of course, to determine this gradient, and for this we provide some backpropagation algorithm for our system, which I will not go into details because we don't have time for that. So that's basically a summary of kind of learning for our network. So if we have here the network, again, input, our first layer, second, third, and output layer, then the green lines are those weights which are determined by the modulation function. So they can be trained. All green lines can be trained. We have one specific feature of our system, that the black weights cannot be trained, and these weights are coming from the discretization. Just maybe if I apologize for joining backwards, I show you what does it mean here. You see that at the discretization, we get that the next node equals to the previous node, and also x of t here is the previous node, and there is no weight here. So this cannot be trained. All others here can be trained, but not this one. And they lead to these black lines in our network, which cannot be trained. And that's why we need some adaptation, some new back propagation scheme to train the network. And finally, it works. And very shortly to summarize, I show you examples of applications, just to some pictures without going too much into details. So you see how if we have handwritten picture 4, what we do in the first step is we multiply it with the input matrix, Wn. We get some other like vector, which we see here. Okay, this digit we kind of vectorize, yeah? We make out of this digit, we make a big vector, multiply the matrix, we get another vector, which you show here. We crop this vector to a certain range and make a data signal j of t in the same way I explain you in the preprocessing stuff. Yeah? And then given this signal j of t, it comes into the like network, DNN, and then the output of the system, XL, from the last layer is multiplied by the output matrix, and then we get another activation output, some vector, and then so-called softmax procedure, softmax classical map applied to this vector gives us the answer. And you see that like 0, 1, 2, 3, 4 on the fifth digit of this vector is 1.0, so it's correctly identified in the input vector 4. So this is just an example. Just to will flip very quickly the slides. This was MNIST classification task, handwritten digit recognition, but one can also apply it for fashion MNIST task or cropped street view house numbers from Google database, or even more advanced CIFAR-10 database for classification. This is interesting how CIFAR-10 classification task looks like. We have 60,000 images, and these images should be classified accordingly to 10 classes, like airplane, automobile, bird. And sometimes classification is very difficult. You see just an example, 3 examples of the bird class, and that's so system should learn how that these 3 pictures, for example, belong to the same class, and that's why this is a very challenging task. Also denoising tasks so that we have some pictures, noisy pictures, and then one should recover this. I will skip this, just some numbers, but this is rather for machine learning experts. So you see some good numbers for MNIST, for more simple tasks, less good numbers for more challenging tasks, but still they are, of course, they're showing also that this works, because this is much higher than just a random choice of application. So to summarize, in my talk, I show you examples of applications of the dynamical system, and in particular delay systems in various machine learning tasks, starting from reservoir computing and then going to deep neural networks. So thank you very much for your attention, for your questions during the talk. Hope you get some more questions now. Thank you.
Thank you, Professor. So the form is open for questions, clarifications, doubts.
Serhiy, may I start?
Yeah, Fernando, you may rise.
Professor, I'd like to know what is the role of the reservoir in the learning process? Since the reservoir is not trained, so what the reservoir is doing in this learning process?
Yeah, this is a very complicated question, yeah, because but I try to maybe give a couple of obvious questions. I don't know if it is sufficient, but let me try. Yeah. So if we have an input, one of the main features of some machine learning schemes is to first to project the input vector in sufficiently high dimensional space, so that then we can classify make classification. For example, about classification. For example, if I don't have these pictures, usually there are nice pictures showing how this high dimensional projection is important for classification. So if you have data, you have data on a 2-dimensional projection, then you cannot find a line which separates nicely the data. But if you project this data in a high dimensional space, you can find a plane which separates the classes of the data. So that's why this projection into higher dimensional space is important. And the reservoir is acting like this projection in a high dimensional space, because usually the reservoir is a large network or time delay system, which is also infinite dimensional. Yeah, so that's why it's a projection. It's a first, but also a second, it acts as a memory. Now, because if you put the input signal in the system, then the information keeps going in the system if it is a large network, or it's if a delay system. Yeah, then it inside the delay loops or inside the network, it circulates, and that acts as a memory. So as an output, you can use this memory. Yeah, that's important sometimes for the tasks. Okay, that's probably the first which comes to my mind, but definitely there are many others properties which which reservoirs.
Okay, thank you.
Thank you for the question.
Okay, Prasad, you can raise your question.
Yes, so actually I have some question from basic actually. So I was trying to understand that like you told that there is
No, Prasad, your voice is not clear.
There are probably some problems with connection. We cannot hear, right?
Or can you write your question in the chat box?
Hello?
Prasad?
Is it a problem with connection on my side or?
No, the other side.
Okay.
Sir, I am audible now, sir?
Yes, Prasad, go ahead.
Okay, sir. Actually, my question was a bit from basics, sir. So, like, I was thinking that, here we are talking about the single neuron, which is evolving in time frame, and future states are connected by previous states. Is it, sir? Like, the states are thought of as a node, sir. So, is it? If I'm right.
This is correct. Yes.
Okay, sir. Like in the one of slides, you have told that if we think of like one state as a like in the form of some matrix, and the next state in the form of another matrix. So those two matrix shows some kind of synchronization also. Like future states is synchronized with the previous state. That kind of conclusion I'm doing if
I'm thinking where I was speaking about this. Do you mean generalized synchronization?
Yes, sir. Like the synchronization.
Okay, I'm looking for. Do you mean this slide? Yeah.
Yes, sir. Is it synchronization between future and previous states, sir?
No. It's not synchronization between previous and future. This is so-called generalized synchronization under the external input. So it basically means that if you have the same input given to your system at different occasions, you have your system, you give your input of some certain input, then the system reacts to the input in a certain way, and it is independent on the initial state of the system X. So independently on initial state of system X, your reaction to the input will be asymptotically the same. And this is in this slide, I just show this. This is how one can compute this. One has one system like reservoir X1, input Z, and one makes a copy of such system like X2 dot equals to f of x2 z of t. It's just the same system as this one, but it can have different initial conditions. And then the synchronization between these two copies is the generalized synchronization. But that does not imply the synchronization between previous layer and the next layer or whatever.
So because I got this confusion because in the future slides it was told that you have divided a time interval, and the previous time interval is connected with the future time interval, like the nodes are connected. And so why we are not taking the neighbor nodes, sir? Is it because we want to distinguish the layers, or what's the?
We take also neighboring nodes. I mean, look at this connection. So like here, we have a connection due to the delay, but also we have a connection from the neighboring nodes. Here probably one should also make a error between the neighboring nodes. That's what we do here. You see, that's the connection between the neighboring. Do you mean this connection? Like the connection from X11 to X21?
Okay, sir. So the neighboring, okay, so the connection between neighboring nodes will not give any delay, sir. Is it?
Yeah, here these connections, this neighboring connection, just appear not because of delay, but because of the like inertia. Yeah, so it's like a previous node. It's like in ordinary differential equation. Like if you know the previous node, you find the next one. So that's then you have a connection to the previous node only. And here we have the same like for ordinary differential equation, this black line, and then additionally the colored line comes through the delay.
Delays.
Yeah.
Okay. Another things like so you told about at the starting some ledger system. So using the ledger system, like some kind of delay you were talking about. So I didn't get that point actually, sir. So is it like getting like giving a delay in the photons, like in the term of their frequency or what, sir?
So you can imagine this setup, a certain laser setup. Let me think. Can I? No, I cannot. I cannot kind of draw here. But you can imagine here some like a laser, and then you can imagine feedbacks from laser in form of a glass fiber. Yeah, this laser light goes out, and with a glass fiber goes through a certain device which modulates and then comes back into the semiconductor laser. You can imagine really like a laser with external glass fiber which put the light from the laser and put it backwards. But of course, I'm not a specialist in experiment. One of our co-authors, Ingo Fischer from Palma, from Spain, he's a brilliant experimental scientist who implementing also such laser system. We did not implement this yet, but that's would be also possible to imagine. And some laser with delayed feedback.
It's kind of like a deep neural network using the photons.
Yes, that's yeah,
Yes.
that's true. Also, there is a big field of science now which is very active, like neuromorphic computing.
Okay.
That's true, and this would be a possible realization then.
Okay, and another thing, like in the input weight, you told that it could be random. It's not need to be trained one. So is there a particular reason behind it? And is there anything that we need to train the input also? Like
You mentioned random input weights, right?
weights, yes.
This is for the case of reservoir. This is in the case of a reservoir. Very often, let me go to the reservoir here. The input weights are kind of randomly and fixed, and because the reservoir is considered to be a very simple for the training. That's why in the reservoir only output weights are trained. Everything else, like reservoir input layer, are considered to be fixed because that's the main advantage of the reservoir. They are randomly assigned, and usually it works. And for DNN, we have input weights which are also trained. Yeah, that's the difference.
Okay, sir. Okay, sir. Okay. Thank you so much, sir.
Yeah, thank you for many interesting questions.
So any other question from the audience? Yeah, Sanjay, please go ahead.
Yeah, hi, Professor Yanchuk. So nice, very informative talk. So I have one question. So in the post-processing process, where you reconstruct the vector y, right?
Mm-hmm.
So you use summation over j. So yeah, the first expression. So this j runs from all over the number of virtual nodes, or?
Yes, this j in the first expression, this goes on the virtual node in one layer. So it's basically, for example, for x of 2, this is just a linear sum of the nodes, like this one, this one, this one, this one, this one. Yeah, that's the sum.
So,
and then we
yeah,
get the output y of k, yes.
Right. If j runs from 1 to, throughout the number of virtual nodes, because you stated that the performance will be bad if the time delay resonates with the clock cycle.
Sorry, there was some break in the signal. Can you please repeat your question?
Yeah, if this J runs all over from 1 to n, where n is the number of virtual nodes, then that corresponds to the total delay of the system. Am I right?
That's, you assume now that the t equals to the delay, right? In your question.
And yeah, I'll come to that later. But if this J runs from one, I mean, a number of virtual nodes, the total will be equal to the time delay of the system.
No, the total. So these are virtual nodes in one clock cycle, and the clock cycle is usually should usually not be equal to the delay. There are some earlier works which have been using the fact that this choice that t, the clock cycle, equal to the delay, but that is shown to be not optimal. That's why we usually assume that t is not the delay. And that's why if you consider all the virtual nodes from 1 to, let's say, n or whatever, then you don't get one delay interval, but you get something else, slightly deviating.
Maybe plus minus tau, whatever.
No, you get t, which is different from tau. But usually, from practical reason, t equals to tau plus some not very big number. So it's around tau, but not equal. Then otherwise we get resonance.
Yeah, fine. Yeah,
but was that okay? Thank you.
Yeah. And when it comes to the generalized synchronization, you have shown this, I think, on previous slide where you have shown conditional Lyapunov experiment and the bifurcation structures. It is nice to see that the bifurcation, basically this bifurcation lines matches with the performance, reservoir performance. So is there any specific type of bifurcation which has high correlation with the memory performance? Or?
Yeah, okay, thank you for this question. We're also happy to see this, how bifurcation analysis and nonlinear dynamics help to understand the reservoir. And so these bifurcations are basically Hopf bifurcation or saddle node bifurcation. But what we observed, the most important is that performance, first obvious is that performance drops significantly if after the bifurcation, if we lost the generalized synchronization, like here in this white region, the performance is kind of dark, bad. But there is another remark, is that close to the bifurcation, we have a yellow here, or here we have close to the bifurcation like yellow, which means high performance, or here, high performance. This yellow, I'm sorry, I mean this yellow, of course. Yeah. This yellow is close to the bifurcation, means high performance here, also high performance here, and it is correlated somehow in a very intuitive, very rough approximation to the small conditional Lyapunov exponent close to the bifurcation. So the performance is high, close to the criticality, if you want, close to the bifurcation, but not behind. And that's a balance. Yeah, you want to be close to the bifurcation, but you don't want to be behind the bifurcation. That's interesting. You have that. And which bifurcation? It's then not, at least from this analysis, it does not show up which bifurcation is the most important. Both saddle node and Hopf leads to similar kind of conclusion.
So then this gives a prescription of about this parameters where we can have best performance.
Yes. So, and very roughly, you should be close to the loss of generalized synchronization, close to the bifurcation, but not behind. Yeah. And maybe practical reasons should tell us that not too close because of the noise can kick us outside, etc. That's the interesting point.
Yeah, it's very interesting to see such correlations. Yeah. Thank you very much. Thank you.
Thank you. We had already quite many questions.
Yeah.
Great. Thank you.
So I'm not receiving any questions. So since there is no questions, let us conclude the session. So I would like to conclude the session by thanking Professor Serhiy Yanchuk for giving a very interesting talk, and many people have raised questions and clarified their doubts. I'm very happy. Thank you, Professor. Thank you very
Thank
much.
you very much, Professor Lan, for invitation. Thank everybody for participation and asking really nice questions. I enjoyed very much. Okay.
Okay. Thank you, Professor.
Okay. Bye.
Bye.
Have a nice day.